Let us discuss the different types of energies which are important for this chapter. So, although there are many types of energies, for this chapter, work energy and power, we are going to discuss the two most important energies. One is the kinetic energy, and then we have the potential energy. The formula for kinetic energy is half mv square. It is represented by K. Potential energy is of two types. First, we are going to consider the gravitational potential energy, and then we have the elastic potential energy. Gravitational potential energy is the energy of an object because of its height. And the formula for that is m into g into h, where m is the mass, g is the acceleration due to gravity, and h is the height of the object. On the other hand, elastic potential energy comes into the picture when we have springs. So when a spring either compresses or it stretches, then we say that elastic potential energy is stored inside the spring. And what is the formula for that? Elastic potential energy is given by this formula, half kx squared. Now let us analyze each of the potential energies one by one, starting with gravitational potential energy. Now consider this image. We have an object apple which has been lifted up by a distance h. So initially the apple was on the ground. So we have labeled that by point A, and the topmost point is labeled B. So the distance between A and B is h. Now, in order to solve questions, it is very important for us to understand a concept called the reference line. Now, what does that mean? So let's read. A reference line is basically a point where the gravitational potential energy is assumed to be zero, and that's the reference line. So the ground in this case will be a zero potential energy. Hence, we can say that if the object were at A, which is on the ground, the potential energy for the apple on the ground would have been zero. After that, let's read this. Points above the reference line have positive potential energy. So over here, the point B is above the reference line. So potential energy will be positive mgh, which I have represented here. On the other hand, if you have points which are below the reference line, they have negative potential energy. So let's look at the same image. We have the apple, but under the ground or below the ground. In this case, the distance between A and C is h only, the same as above. So the magnitude of the potential energy will still stay the same, mgh, but it will have a negative sign. So potential energy of the apple at the point C will be equal to negative mgh. Now, why do we put a minus sign? Because the object is under the reference line. And while solving questions which deal with potential energy for this chapter, it is very important for us to analyze what is the reference line. So if we go above the reference line, potential energy will be positive. Below the reference line, potential energy will be negative. So this was all about the gravitational potential energy. The formula is mgh, but we need to be careful about the sign. Next off is elastic potential energy. We already know elastic potential energy will come into the picture if you have springs. If a spring either compresses or it stretches, then we say that the spring has stored elastic potential energy. So the formula for this is half kx square, where k is a constant dependent on the type of the spring. So k is the spring constant, and x, on the other hand, is compression or extension in the spring. So how much the spring has compressed or stretched, that is x. So imagine a situation if the spring is stretched a lot, so the value of x will be greater. So the spring would store a lot of elastic potential energy in that case. Now, just based on this formula, let's solve a quick question. So let's read. We have a spring in relaxed position which is extended by 0.4 meters. The spring constant is given, and we need to find the elastic potential energy stored in the spring. So what is meant by relaxed position? So remember, relaxed position is the spring is neither stretched nor it is compressed. So it is in its natural length. Now, if you recall, the formula for spring force, let us write, is given by the Hooke's law, which is k into x. So if the value of x is 0, which means the spring is neither stretched nor it is compressed. So if the value of x is equal to 0, that is what we call as the relaxed position. So in that case, the spring force will be 0, and hence we say the spring is in the relaxed position, as no pulling or pushing force is being exerted on the spring. So that was the description of this word relaxed position. Now let's analyze. We have to figure out the elastic potential energy. So the formula is half kx square, right? So half kx square. Now the value of k, the spring constant, is already given 48, and the extension is also given 0.4. So that's it. Just put all the values in, and eventually we will get 3.84 joules. Hence, the elastic potential energy stored in the spring is positive 3.84 joules. All right, let's solve another question based on this logic of half kx square. Here we have a spring of spring constant 100 newtons per meter. It is compressed by 6 meters, as you can see in this diagram. A box is placed against the spring. At the point where the box has moved by 2 meters, how much elastic potential energy is stored in the spring? So we already know the formula for potential energy is half kx squared. So let's analyze this question properly. So consider this image on the bottom. Initially, the spring was compressed by 6 meters, as you can see in this image. In the second situation, the box has moved by 2 meters. So let me explain that. So consider this red line is the original position of the box in case 1. In case 2, the box has moved a little bit to the right hand side by 2 meters, as they have given in the question. Now the box has moved by 2 meters, which means there will be a change in the compression of the spring. And now we have to figure out the potential energy, which is half kx square. The value of k is already given to us as 100. So all we need to figure out is the extension or compression in the spring in the case 2. So initially in case number 1, we saw the spring was compressed by 6 meters. So initial compression is 6 meters. But what will be the final compression is case 2. Please do not assume 2 meters as the final compression in the spring, because if you analyze in the case 1, this 6 meter was the total compression. How do you find the compression or the value of x? We find the distance of the box from the relaxed position. So that is why initial compression in the spring was 6 meters. In case number 2, we have to figure out the distance of the box from the relaxed position. So this arrow is the final compression in the spring. So how do we figure that out? Total distance is 6 meters, out of which box has gone to the right 2 meters. So this will be 6 minus 2, which comes out as 4 meters. So we can write down the final compression in the spring is 6 minus 2, which is 4 meters. And that's it. Now we have all the parameters required. K is 100. The final compression is 4. And if we simplify this, we will get 800 joules as the elastic potential energy stored in the spring. Next, we have the total work done by the spring. So to find the work done by the spring, if you try to recall the most basic formula for work, which was Fs cos theta. Now try to think, can we even apply this formula to find the work done? The answer is no. And why is that? Let's read. We cannot apply this formula to find the work done by the spring since the value of F is not a constant. So let us try to recall. This formula of Fs cos theta is only applicable if all the parameters involved, like force, displacement, theta, everything should be constant. But in this case, if you remember the spring force formula, which is the Hooke's law, Fs is equal to Kx. So you can see the value of the spring force depends on x. So higher the compression or extension in the spring, more will be the spring force. So clearly the spring force is not constant. Hence, we cannot apply this formula. So if a question asks us to find what is the total work done by the spring, so we cannot apply this formula. So what do we do in that case? We have another formula which we need to remember. So work done by the spring is given by this formula. It is equal to negative of the change in elastic potential energy. On the other hand, if we have to figure out the work done on the spring, so the magnitude will still stay the same, but we will remove the negative sign. So work done on the spring is given by the formula positive change, delta is change of elastic potential energy. And the change in elastic potential energy, remember, is final minus initial. So we can write delta EPE is equal to the final elastic potential energy minus the initial elastic potential energy. And now we can summarize all the formula. Work done by the spring is given by the formula E initial minus E final. So why we have done initial minus final in this case? Because work done by the spring was equal to negative of the change in elastic potential energy. And because of the minus sign, we have written initial in the first place and final in the last. So while solving questions, be very careful. Is the question asking you to find work done by the spring or on the spring? So this was the formula for work done by the spring. In the case the question is find the work done on the spring, it is positive delta EPE, which will be just final minus initial. And now we can simplistically deduce that work done on the spring is equal to negative of work done by the spring. And now let us try to solve questions on springs. We have to figure out the work done because of the spring. So be careful in the question. You need to analyze, is the question asking you to find work done by the spring or on the spring? Depending on that, we will use the